The Hubble Space Telescope has photographed galaxies billions of light years away, but it has a hard prohibition in its scheduling software against ever pointing at Mercury, because the Sun is close enough that a slight misalignment could destroy its optics in seconds. Subscribe if you want more of the cosmos. This is White Space Settle-In. Of all the planets in our solar system, the one closest to the Sun remains among the least understood. Mercury sits at an average distance of only 58 million kilometers from our star, a proximity that grants it a kind of invisibility from our perspective. It never strays far from the Sun as seen from Earth. Observers can only catch it for a narrow window each evening just after sunset, or each morning just before dawn, always hovering near the horizon, never climbing high enough to be studied comfortably. Most people have never seen Mercury with their own eyes, and even those who know exactly where to look will find a pale, trembling point of light that refuses to yield its secrets. The challenge is not merely one of timing. Even the most powerful ground-based telescopes struggle to resolve meaningful detail on Mercury's surface. The planet is small, roughly 40% of Earth's diameter, and the optical distortions introduced by Earth's atmosphere compound the difficulty. Whenever a telescope is pointed low toward the horizon, which is where Mercury always lives, it peers through a much thicker column of air than when pointed overhead, and that air shimmers and smears the image. The Hubble Space Telescope, which has captured images of galaxies billions of light years distant, has never been pointed at Mercury. The reason is simple. The angular separation between Mercury and the Sun is small enough that even a momentary misalignment could allow concentrated sunlight to strike the telescope's optics. The result would be catastrophic damage to instruments worth hundreds of millions of dollars. So Mercury, the nearest planet, remains off-limits to our most capable orbital observatory. There is something almost poetic about this. A planet so close to us that it has been known since antiquity, named by cultures across Mesopotamia, Greece and Rome, still holds secrets that the most sophisticated telescope ever built is forbidden from probing. It was radio astronomy that first gave scientists a meaningful foothold. Ground-based radar systems bounced signals off Mercury's surface, beginning in the 1960s. And the echoes came back carrying information that upended long-held assumptions. For nearly a century, astronomers had believed Mercury rotated once per orbit. Keeping one face permanently toward the Sun in a state called synchronous rotation, much like the Moon keeps one face toward Earth. The reasoning seemed sound. Tidal forces exerted by the Sun over billions of years should have slowed Mercury's spin until it matched its orbital period. Radar measurements shattered that picture entirely. Mercury actually rotates 3 times for every 2 orbits around the Sun, a configuration called a 3-to-2 spin-orbit resonance. This means a single solar day on Mercury, the time from one sunrise to the next, lasts 176 Earth days, which is longer than the planet's orbital period of 88 Earth days. A visitor standing on Mercury's surface would experience a sun that rises, moves slowly across the sky, reverses direction briefly as orbital mechanics compete with rotation, then continues to set all over the course of months. This unusual resonance produces some of the most extreme temperature swings in the solar system. The sunlit hemisphere can reach 430 degrees Celsius, hot enough to melt zinc and tin. The night side plunges to negative 180 degrees, a span of 600 degrees on a single planet. The reason for this extreme contrast is the near total absence of an atmosphere. Earth's atmosphere acts as a thermal blanket, carrying heat from the day side to the night side and moderating temperature extremes. Mercury's atmosphere is so thin that scientists call it an exosphere, a tenuous scattering of atoms liberated from the surface by solar radiation and meteorite impacts. far too sparse to redistribute heat at the poles. Where sunlight never arrives due to the planet's nearly vertical axial tilt, permanently shadowed crater floors hold temperatures around -200 degrees, cold enough to preserve ice that has accumulated there over billions of years, delivered by comets and asteroid impacts. The existence of this polar ice remained controversial for decades because it seems so paradoxical on a planet so close to the Sun. But radar observations from Earth in the early 1990s confirmed highly reflective material at both poles consistent with water ice, and subsequent spacecraft observations confirmed it directly. Mercury is also geologically unusual in ways that go beyond its temperature extremes. It is the densest planet in the solar system after Earth, and its density implies an iron core of extraordinary proportions. While Earth's core makes up about 32% of its total mass, Mercury's core accounts for roughly 85%. The planet is essentially a metal ball wrapped in a thin shell of rock. Running along Mercury's surface are enormous cliffs called lobate scarps, some stretching for hundreds of kilometers and rising up to 3 kilometers high. These were formed as Mercury's interior cooled and contracted after its formation, shrinking the planet overall and buckling and crumpling the crust the way the skin of a drying apple wrinkles as the fruit inside shrinks. The total amount of surface shrinkage implied by the lobate scarps is several kilometers across the planet's radius, a sign that Mercury has been cooling steadily throughout its history and has lost an enormous amount of internal heat over 4 billion years. The first spacecraft to visit Mercury was Mariner 10, launched in November of 1973. It carried out 3 flybys of the planet across 1974 and 1975, and in doing so covered a remarkable 45% of Mercury's surface with its cameras. More significantly, Mariner 10 pioneered a technique that would become standard in planetary exploration, the gravity assist. The spacecraft swung past Venus in February of 1974, using the planet's gravitational field to redirect and accelerate itself toward Mercury, without burning additional propellant. This was not an accident of trajectory. It was the result of deliberate mathematical planning by Giuseppe Colombo, who recognized that after the first Mercury flyby, the spacecraft could be placed on an orbital path around the Sun that would bring it back to Mercury twice more. Mariner 10 also detected Mercury's magnetic field, a discovery that surprised scientists because a planet so small, with a rotation so slow, was not expected to sustain the interior dynamo responsible for generating planetary magnetism. The magnetic field is weak, only about 1% of Earth's, but its very existence implies that some part of Mercury's core remains molten and in motion, which itself tells us something important about the planet's thermal history and internal composition. The second mission to Mercury arrived more than 3 decades later. Messenger, the Mercury surface, space environment, geochemistry, and ranging spacecraft, launched in August of 2004. And did not enter orbit until March of 2011. After a journey that included 1 flyby of Earth, 2 of Venus, and 3 of Mercury itself, each one using the planet's gravity to slow the spacecraft enough to be captured. Getting into orbit around Mercury is counterintuitively difficult. The spacecraft is falling toward the Sun the whole time, and it arrives at Mercury moving very fast. To slow down enough to be captured by Mercury's modest gravity requires a large engine burn, which in turn requires carrying enormous quantities of propellant. The gravity assist approach reduces how much propellant is needed, but the price is years of travel time. Once in orbit, Messenger spent 4 years systematically mapping the entire surface and measuring the planet's composition, gravity field, and magnetic environment. It confirmed that the poles hold water ice trapped in those permanently shadowed craters, covered in some cases by a thin layer of dark organic material deposited by the same cometary impacts that delivered the ice. The organic layer acts as an insulating blanket, slowing the sublimation of ice from below. Messinger also revealed that volcanic activity had once been widespread across Mercury's surface. Vast plains of solidified lava, some of them kilometers thick, cover much of the northern hemisphere, erupted in massive outpourings that resemble flood basalt provinces on Earth. The youngest of these volcanic plains may be only 3 billion years old, suggesting that Mercury remained volcanically active for over 1 billion years after its formation. Hollows, small irregular depressions with bright halos, found in certain geological units, appear to form when volatile compounds in the surface rock sublimate directly into space under solar heating, leaving behind pitted, crumbling ground unlike anything seen on the Moon or Mars. The nature of those volatile compounds is still being debated. The third mission to Mercury is currently underway. Bepicolombo, a joint project between the European Space Agency and the Japan Aerospace Exploration Agency, launched in October of 2018 and is named in honor of Giuseppe Colombo, the same mathematician and engineer whose insights enabled Mariner 10's multiple flybys. Bepicolombo consists of 2 separate science orbiters that travel to Mercury together, stacked inside a transfer module, and will separate upon arrival to enter different orbits around the planet. The Mercury Planetary Orbiter, built by Europe, will study the surface, interior and exosphere from a low polar orbit at altitudes between 480 and 1500 kilometers. The Mercury Magnetospheric Orbiter, built by Japan, will study the magnetosphere and surrounding plasma environment from a highly elliptical orbit that takes it as far as 11,000 kilometers from the surface, providing a broader view of how Mercury's magnetic field interacts with the solar wind. Together they carry 23 scientific instruments, more than any previous Mercury mission. Bepicolombo made its first close Mercury flyby in October of 2021, passing within 200 kilometers of the surface and capturing images that showed vast lava plains, ancient impact craters filled by younger volcanic flows, and the prominent scarps that record the planet's slow contraction. Subsequent flybys in 2022-2024 brought the spacecraft progressively closer to its final insertion orbit, and the full science mission will begin at Mercury orbit insertion, generating a volume of data that will rewrite our understanding of the innermost world. While engineers were still dreaming of reaching Mercury, the Soviet Union had already decided it was time to land on Venus. That ambition was born in the late 1950s, at a moment when Soviet space exploration was riding a streak of improbable successes. The first artificial satellite had already circled the Earth. Living organisms had been launched into orbit and returned safely. The far side of the Moon had been photographed for the first time in history. Luna 1 had become the first spacecraft to escape Earth's gravity and enter solar orbit. Against that backdrop, a landing on another planet seemed like the next logical step, a demonstration that Soviet technology and scientific ambition had no practical ceiling. In December of 1959, the Soviet government issued a formal directive to develop spacecraft for missions to Venus and Mars, with launches planned as early as 1960. The ambition was extraordinary. The knowledge to support it was almost non-existent. At that time, scientists genuinely did not know what Venus was like. The planet is perpetually shrouded in clouds, and beneath those clouds almost anything seemed possible. Some believed the surface might be warm and humid, perhaps even hospitable to life. Serious scientific literature from the era included drawings speculating about Venusian vegetation and fauna. Reports circulating in both American and Soviet scientific communities took the possibility of extraterrestrial life in the inner solar system seriously enough to include it in mission planning documents. It would take a decade of punishing failures and gradually accumulating data before anyone had a clear picture of Venus as it actually is. The Venera program began with repeated catastrophe. Venera 1, launched in February of 1961, lost radio contact with Earth 7 days after launch and drifted silently past Venus at a distance of 100,000 kilometers. Over the following years, launch failures, trajectory errors, and premature spacecraft deaths mounted. The engineers were not incompetent, they were working in the dark. The planet they were trying to reach had never been measured directly, and every assumption they built their designs around turned out to be wrong. Venus's atmosphere is not thin and breathable. It is a crushing column of mostly carbon dioxide, dense enough to exert a pressure at the surface nearly 100 times greater than Earth's atmospheric pressure at sea level. The temperature at the surface is not warm and tropical. It is around 465 degrees Celsius, hot enough to melt lead, sustained by the most extreme greenhouse effect in the solar system. Sulfuric acid clouds begin at an altitude of about 45 kilometers and extend upward to about 70 kilometers, creating a chemically hostile environment that corrodes metals and destroys conventional electronics. Venera 4, which reached Venus in October of 1967, transmitted data for 94 minutes during its atmospheric descent before failing. The probe was crushed before it reached the surface, but the data it transmitted was the first direct measurement of another planetary atmosphere in history, confirming that Venus's air is predominantly carbon dioxide. Venera 5 and 6 in 1969 met the same fate, destroyed by pressure before touchdown, but each one added more data points to the picture scientists were assembling. By 1970, engineers finally understood what they were dealing with. They redesigned the descent capsule from the ground up, building it to withstand 180 atmospheres of pressure and temperatures above 500 degrees for at least 90 minutes. The capsule was machined from titanium rather than aluminum, which added mass and forced engineers to remove several scientific instruments but gave it a fighting chance. It weighed 500 kilograms, small enough to be launched from a Proton rocket, but robust enough. Its designers hoped to reach the ground intact. Venera 7 launched from Baikonur on August 17, 1970. A backup spacecraft launched 5 days later but never left Earth orbit, its upper stage failing at a critical moment. The original probe took 120 days to reach Venus and entered the atmosphere on December 15, 1970. The descent sequence did not go as planned. The parachute partially failed, tearing under aerodynamic stress much sooner than the design intended, and the capsule fell faster than planned through the lower atmosphere. The telemetry system also failed. The only instrument that continued transmitting during the descent and landing was the temperature sensor. Scientists on the ground received a signal, but they could not decode it in real time. It was only later, when engineers went back through the raw radio data and amplified a very weak carrier signal that had shifted slightly in frequency, that they discovered 23 minutes of temperature readings originating from the surface of Venus. The temperature was 477 degrees Celsius. Venera 7 had landed. It was the first human-made object ever to return data from the surface of another planet. The missions that followed steadily expanded what was possible. Venera 8 in 1972 confirmed that light penetrates the lower atmosphere well enough for cameras to function on the surface, and measured wind speeds at the surface of roughly 1 meter per second. The thick atmosphere, despite its violence in the upper cloud layers where winds circle the planet at 360 kilometers per hour, moves very slowly near the ground, more like a dense liquid than a gas. Venera 9 and 10, arriving in 1975, returned the first photographs ever taken from the surface of Venus. Black and white panoramic images showing angular plate-like rocks strewn across a landscape that looked like a demolished quarry under an overcast sky. No dust, no smooth sediment, just fresh-looking broken rock. The geological youth of the surface implied by those jagged edges was itself a clue. On Venus, erosion by wind or water barely operates at all, so surfaces can retain sharp features for millions of years longer than on Earth. Then came Venera 13 and 14 in 1982, the most sophisticated landers the Soviet Union ever sent to another world. Each spacecraft carried 14 scientific instruments, including mass spectrometers, gas chromatographs, X-ray fluorescence spectrometers, accelerometers, seismometers, soil sampling drills, and cameras capable of capturing color panoramas. Venera 14 separated from its orbital module and entered the Venusian atmosphere on March 5, 1982. The descent was a precisely choreographed sequence of thermal management and atmospheric braking. The capsule, encased in a spherical aeroshell 2.5 meters in diameter, hit the upper atmosphere at 11 kilometers per second. A drogue parachute deployed to slow the initial phase of descent through the upper cloud layers, where the temperature is still manageable. At an altitude of 47 kilometers, the parachute was jettisoned. Below that level, the atmosphere is dense enough that the capsule's own aerodynamic drag slows it adequately, and the parachute would only have extended the time the probe spent in the most corrosive part of the cloud layer. The capsule descended the rest of the way under a disc-shaped aerodynamic brake, carrying enough thermal mass in its structure to absorb the heat without catastrophic failure. The entire descent from atmospheric entry to touchdown took about an hour. At the moment of final approach to the surface, the onboard microphones were activated. What they captured was the only audio recording ever made on the surface of Venus. A deep, resonant droning with fluctuating overtones, the sound of a slow, stupendously dense wind moving through an atmosphere 90 times heavier than Earth's, under a sky perpetually lit by the indirect glow of sunlight filtered through kilometers of sulfuric acid cloud. It is an alien sound in the most complete sense, and it remains unique in the entire archive of planetary exploration. Venera 14 landed in a region called Phoebe, nearly 1,000 kilometers from the twin lander Venera 13. The color panoramas it transmitted showed flat, layered rock outcrops and dark, fine-grained sediment, a landscape geologically distinct from the jagged rubble seen at earlier sites. The rocks looked stacked and stratified, suggestive of material formed under sustained heat and pressure rather than rapid volcanic quenching. Analysis of soil samples collected by a drill and delivered to an onboard chemical laboratory confirmed the surface rock is compositionally similar to oceanic basalt found on Earth's ocean floors, the kind of rock produced by basaltic magma erupted under conditions of high pressure. From a planetary geology perspective, this was an important data point in the debate about whether Venus's interior is still churning, still producing fresh material. The lander was designed to operate for 32 minutes in those conditions. It functioned for 57, transmitting continuously in 466-degree heat under 94 bars of pressure, before the signal finally went silent. These images remain to this day the only photographs taken from the surface of Venus. No subsequent mission has landed on the planet. The total record of direct Venusian surface measurements from all Venera landers combined amounts to a few hours of data spread across several widely separated sites. We know more about the surface of Mars from individual rovers that have operated for over a decade than we know from the entire combined history of Venus surface exploration. The reasons are not lack of interest, but engineering reality. Building hardware that can survive on Venus long enough to accomplish meaningful science is one of the most difficult challenges in the entire field of planetary engineering. Scientists have proposed landers made from high-temperature electronics, from silicon carbide chips that can withstand Venusian temperatures without cooling, from mechanically actuated systems that use no semiconductor electronics at all. None has yet flown. New missions are in development, including NASA's Jansky probe, which will descend through the atmosphere, measuring its chemistry in detail, and Veritas, which will map the surface from orbit using radar imaging. Whether they will answer the deepest question that Venera raised, whether Venus was once more like Earth, whether it had oceans and a moderate climate before the greenhouse ran away, remains to be seen. Far beyond the inner planets in the cold outer reaches of the solar system, a different kind of explorer spent 20 years conducting what may be the most ambitious single scientific investigation in the history of spaceflight. Cassini-Huygens launched in October of 1997 on a Titan E-Ver rocket from Cape Canaveral, carrying the heaviest planetary probe ever launched to the outer solar system at the time. It traveled for nearly 7 years across more than 3 billion kilometers, executing gravity, assists around Venus twice, Earth once, and Jupiter once, each time gaining speed from the planet's orbital motion without burning propellant. The spacecraft entered orbit around Saturn in June of 2004, firing its main engine for 96 minutes to slow down enough to be captured by Saturn's gravity. An engine burn that had to succeed perfectly, or the mission would end then and there. It succeeded, and for the next 13 years Cassini circled the planet, its moons and its rings, returning data that will be analyzed for generations. Saturn presents itself as a kind of solar system in miniature. The planet itself is a gas giant 11 times wider than Earth, with an interior that transitions from hydrogen gas in the upper atmosphere to liquid hydrogen, then to a form of metallic hydrogen in which electrons flow freely through the fluid under enormous pressure, behaving like a conducting metal, generating Saturn's global magnetic field. The planet rotates in just over 10.5 hours, fast enough that its equator bulges visibly outward and its poles are measurably flattened. Around it orbit 82 confirmed moons, ranging from tiny moonlets embedded within the rings to Titan, a world larger than the planet Mercury. Wrapped in a thick nitrogen atmosphere dense enough that its surface pressure is 1.5 times Earth's atmospheric pressure. Titan's surface temperature is negative 179 degrees Celsius, cold enough that methane exists there as a liquid, filling lakes and seas in the polar regions, carving river channels, evaporating to form clouds, and raining back down in what is the only active hydrological cycle in the solar system apart from Earth's, except that the working fluid is not water but methane. The Cassini mission carried the Huygens probe, built by the European Space Agency, which detached in December of 2004 and entered Titan's atmosphere on January 14, 2005. It descended for 2 hours and 27 minutes under a parachute, becoming the most distant object ever landed in the solar system at the time, and transmitted data for 72 minutes after touchdown on a surface of solid water ice pebbles rounded by fluid flow. The images Huygens returned show the landscape of dark plains intersected by bright highland areas, with features that looked unmistakably like drainage channels carved by flowing liquid. The atmospheric chemistry Huygens measured confirmed the presence of complex organic molecules, including nitriles and hydrocarbons, built up over billions of years by ultraviolet photochemistry in the upper atmosphere. Titan's chemistry may be a slow-motion preview of the chemistry that operated on the early Earth before life emerged, playing out under conditions that preserve the molecules indefinitely because nothing biological is consuming them. As Cassini's fuel reserves dwindled in 2017, mission planners designed a final sequence of observations called the Grand Finale. Beginning in April of that year, the spacecraft was directed onto a new trajectory that took it through the gap between Saturn's innermost ring and the cloud tops of the planet itself, a region no spacecraft had ever entered. The gap is roughly 2,000 kilometers wide. No one knew exactly what to expect in terms of particle density. The region might contain debris dense enough to damage or destroy the probe. Mission controllers decided to use the large dish antenna as a shield during the first dive, pointing it into the direction of travel to protect the more sensitive instruments. The gap turned out to be largely clear, and Cassini completed 22 of these ring gap orbits across 5 months, each one providing measurements impossible from the more distant orbits that had characterized the previous 13 years. What dominated the mission team's attention during those final passes was the North Polar Vortex. Saturn's North Pole is home to a hexagonal atmospheric feature that has no equivalent anywhere else in the solar system. It is a standing wave pattern in the atmosphere shaped like a regular 6-sided polygon, and each side of that hexagon is roughly the diameter of Earth, making the entire structure several times wider than our entire planet. The hexagon rotates with Saturn's interior magnetic field, completing one rotation in 10 hours and 39 minutes. Exactly the period of Saturn's deep interior rotation, suggesting the structure is anchored to the planet's core dynamics, rather than the surface weather systems. At the center of the hexagon sits an enormous cyclone with an eye 3 times the width of Earth, surrounded by cloud walls that rise several times higher than the walls of terrestrial hurricanes. The hexagon changes color with the seasons. Saturn's axial tilt of about 27 degrees, comparable to Earth's 23.5, means it experiences seasons as it orbits the Sun over a period of 29 years. When the northern hemisphere tilts toward the Sun during Saturn's summer, ultraviolet radiation drives photochemical reactions in the upper atmosphere that create an aerosol haze, tinting the hexagon gold and amber. In winter, when sunlight retreats, the feature darkens to a blue-gray, but its geometric form remains constant. The central vortex holds its dark blue color, independent of the seasonal cycle, apparently because the aerosol particles are drawn inward and downward by the circulation patterns in a way that keeps the eye clear of the tinting compounds. The haze particles settle out in the outer regions but are evacuated from the core of the vortex by the same dynamics that maintain the hexagonal flow pattern. Cassini's final close passes returned images of the hexagon at a resolution never previously achieved, revealing that it is not a single smooth wave but a coherent structure composed of hundreds of smaller embedded vortices, each feeding energy into the larger pattern through turbulent exchange in a way that maintains the overall symmetry for what appears to be centuries. Among the discoveries of the grand finale, one stands out for its implications for the long-term future of Saturn's most iconic feature. Cassini confirmed that the rings are slowly raining onto the planet. The particles that make up the rings are not electrically neutral. Ultraviolet radiation from the sun strips electrons from ice particles in the rings, leaving them with a net positive charge. Saturn's powerful magnetic field then pulls those charged particles along magnetic field lines down into the upper atmosphere at a rate of several tons per second. This ring rain, as researchers call it, is not uniform. It concentrates at specific magnetic latitudes where the field lines from the ring plane intersect the atmosphere, creating banded patterns of enhanced ionization that were measured directly by Cassini's instruments during the grand finale passes. If this process continues at its current rate, the rings will cease to exist within about 300 million years. That is a long time by human standards, but the solar system is 4.5 billion years old, and the rings are a transient feature on that time scale. This finding connects directly to another question Cassini helped answer. How old are the rings? The measurement of ring mass, which Cassini determined precisely for the first time through its effect on the spacecraft's trajectory during the grand finale passes, revealed that the rings contained far less material than had previously been estimated. They are roughly 100,000 times lighter than Earth. That low mass combined with the surprising brightness of the ring particles suggests the rings are geologically young. Old ring material would accumulate dust from the meteorite bombardment that constantly peppers the outer solar system, darkening over time as the silicate and carbon-rich impactors coat the pristine ice. The rings are too bright to be old. The best current estimates put their age at between 10 and 100 million years, meaning that when non-avian dinosaurs first appeared on Earth during the Triassic period, Saturn may have had no rings at all. The most likely explanation involves the destruction of a large icy moon. Saturn's many moons do not orbit randomly. They interact gravitationally with each other and with the rings in complex resonant relationships that have evolved over billions of years. In the early solar system, a moon comparable to Mimas or Enceladus may have migrated inward through gravitational interactions until it crossed the Roche limit, the distance from a planet at which tidal forces become stronger than the self-gravity holding a body together. Inside the Roche limit, Saturn's tidal pull would have torn the moon apart, spreading its ice and rock around the planet's equatorial plane. Mutual collisions among the debris would have ground the fragments down progressively, smoothing rough edges the way river currents polish river stones, producing the fine, bright, ice-rich material that makes up today's rings. The rings are not a uniform sheet but a complex, layered structure. Cassini's measurements showed that the density of ring material varies enormously over very short distances, with dense ringlets alternating with near-empty gaps, with waves and spirals driven by the gravitational resonances of Saturn's many moons. Shepherd moons, small bodies orbiting at the edges of certain gaps, use their gravity to confine the ring material into narrow bands, preventing the edges from spreading and diffusing. The combination of all these interactions, dozens of moons pulling and pushing at billions of particles, creates a dynamic system that is perpetually evolving, never quite in equilibrium, producing patterns of extraordinary complexity from the simple laws of gravity and collision. Cassini fell into Saturn's atmosphere on September 15, 2017, transmitting data until the pressure and heat overcame its systems. The mission had been designed to end this way deliberately to prevent an uncontrolled deorbit that might contaminate Enceladus or Titan, both of which harbor conditions that might support life with terrestrial microorganisms. To the end, Cassini's instruments functioned. The mass spectrometer measured the composition of Saturn's upper atmosphere as the spacecraft descended into it. The ion and neutral mass spectrometer detected organic molecules above the clouds. Each instrument returned data for as long as the telecommunications link held. Then the signal ceased, and one of the most productive scientific missions ever conducted was over. 2 years before Cassini launched, 2 other spacecraft were already in deep space, approaching the outer boundary of the solar system. Voyager 1 and Voyager 2 had left Earth in 1977, and nearly 50 years later, both of them are still transmitting. They are the most distant human-made objects in existence, separated from Earth by more than 20 billion kilometers, and they represent the only direct measurements ever taken of the space between the stars. The journey that led to Voyager began with a calculation made by a summer intern. In 1964, Gary Flandreau, a doctoral student working at the Jet Propulsion Laboratory, was assigned to survey future mission opportunities to the outer planets. While plotting the positions of Jupiter, Saturn, Uranus, and Neptune over the coming decades using a conference room, chalkboard, and hand-drawn graphs, he discovered that in the late 1970s, all 4 planets would be arranged in a configuration that occurs only once every 175 years. A spacecraft launched at the right moment could visit each of them in sequence using the gravitational field of each planet to accelerate and redirect itself toward the next. A technique Flandreau called the Grand Tour. Without this trajectory, reaching Neptune from Earth using existing rockets would have required 30 years. With the Grand Tour alignment, the journey could be completed in 12. The alignment would not recur until the 2050s. Whatever humanity was going to do with this opportunity, it had to do it in the 1970s. The original Grand Tour concept called for 4 large spacecraft, 2 following each trajectory. Budget constraints reduced this to 2 spacecraft, renamed Voyager, which were lighter and more capable than the spacecraft used for earlier planetary missions. Voyager 12 launched first on August 20, 1977, followed by Voyager 1 on September 5, 1977, on a faster trajectory that would cause it to reach Jupiter before its twin despite launching later. Voyager 1 reached Jupiter in March of 1979. The images it returned transformed our understanding of the Jovian system, the Great Red Spot, an atmospheric storm that had been observed telescopically for centuries, resolved into a complex structure of spiraling cloud bands and embedded smaller vortices with a counter-rotating oval hundreds of kilometers across at its center. More startling was Io, the innermost of Jupiter's 4 large Galilean moons. Voyager 1's cameras, during a routine navigational image sequence, caught Io in the act of erupting. 9 active volcanoes were identified in the images, their plumes rising hundreds of kilometers above the surface. Linda Morabito, a navigation engineer at JPL, was the first person to recognize the plume in the images, initially thinking it might be a moon behind Io. It was in fact material erupted from the volcano Pele, rising 300 kilometers into space before falling back to the surface. It was the first time active volcanism had been confirmed anywhere beyond Earth. And it happened not on a world geologists would have predicted to be internally active, but on a moon smaller than Earth's own, kept geologically alive not by residual internal heat, but by the constant tidal kneading of Jupiter's enormous gravity, which flexes Io's interior hundreds of meters on every orbit, generating enough frictional heat to power hundreds of active volcanoes simultaneously. Voyager 1 also discovered a faint ring system around Jupiter, established that the rings were composed mostly of fine dark dust knocked off small inner moons by micrometeorite impacts, and revealed previously unknown complexity in the atmospheres and surfaces of Ganymede, Callisto, and Europa. Europa's surface, a smooth shell of water ice crisscrossed by linear ridges and dark fractures, hinted at a liquid water ocean beneath, insulated by the ice and heated by tidal friction. That hint has grown into one of the most compelling questions in astrobiology, but Voyager could only glimpse it briefly in passing. Saturn was next. In November of 1980, Voyager 1 passed within 64,000 kilometers of Saturn's cloud tops. The rings, which from Earth had always appeared as a few broad bands separated by a handful of gaps, resolved into hundreds of distinct ringlets, with braided structures, kinks, and waves that demanded explanation and would not receive satisfactory ones until Cassini arrived decades later. The temperature of Saturn's upper atmosphere was measured at negative 190 degrees Celsius, while winds at the equatorial belt reached 1800 kilometers per hour. The moon Mimas passed at 88,000 kilometers, displayed the enormous Herschel crater, an impact basin 200 kilometers across covering more than a quarter of the moon's own diameter, a reminder that smaller bodies in the outer solar system have survived extraordinary violence. The most scientifically consequential stop at Saturn was Titan. Voyager 1 passed within 6,500 kilometers of its surface and found an atmosphere far denser than models had predicted. Opaque to visible light, rich in nitrogen and methane and complex organic compounds built up by photochemical reactions over billions of years. The surface temperature of negative 179 degrees Celsius, combined with the atmospheric pressure and methane abundance, implied that liquid methane could pool on the surface. Whether it formed seas, lakes, or merely occasional puddles could not be determined from the flyby data and would not be answered until the Cassini-Huygens mission confirmed methane lakes in 2007. The trajectory that sent Voyager 1 so close to Titan also kicked it out of the plane of the ecliptic, the disk of the solar system, so it could no longer reach Uranus and Neptune. Mission controllers made this trade-off deliberately, choosing Titan data over the remaining outer planets, because Voyager 2 had been designed from the start as a backup and could be redirected to cover those worlds. Voyager 2 arrived at Uranus in January of 1986, returning the first close-up images of a world that ground-based telescopes had shown only as a featureless blue-green disk. The planet proved stranger than anticipated. Its axial tilt of 98 degrees means it rotates nearly on its side, with its poles pointing roughly toward and away from the Sun during solstices. Its magnetic field is tilted 60 degrees from its rotation axis and offset significantly from the planet's geometric center, producing an asymmetric magnetosphere that wobbles dramatically as the planet rotates. Voyager 2 discovered 10 previously unknown moons, each one a dark, geologically complex world, and imaged the moon Miranda, which showed a surface so chaotic, with cliffs 15 kilometers high and ancient heavily cratered terrain juxtaposed against younger grooved terrain in a pattern unlike any other moon in the solar system, that some scientists initially speculated it had been completely shattered and reassembled. Then, 3.5 years later, in August of 1989, Voyager 2 completed the grand tour at Neptune. Neptune had been known from Earth only as a small blue disk, and only its largest moon, Triton, had been identified. Neptune's most striking feature in the Voyager 2 images was a massive oval storm in the southern hemisphere. The Great Dark Spot, roughly the size of Earth, exhibiting anticyclonic rotation. Wind speeds around that storm reached 2,400 km per hour, making Neptune's atmosphere the most dynamically violent in the solar system, despite receiving less than 1% of the solar energy that drives Earth's weather. The energy must come from internal heat. Neptune radiates about 2.5 times more energy than it receives from the Sun, suggesting its interior is still slowly contracting and releasing gravitational energy. Voyager 2 also discovered 6 new moons, confirmed the existence of ring arcs, and found active geysers on Triton, nitrogen gas erupting from beneath the surface in dark plumes that are blown downwind by the extremely thin atmosphere. Triton orbits Neptune in the wrong direction, opposite to the planet's rotation, which strongly suggests it is a captured object from the Kuiper belt rather than a native moon. A world kidnapped by Neptune's gravity in the outer solar system's turbulent early history. With the planetary encounters complete, both spacecraft continued outward. In February of 1990, Voyager 1's cameras were turned back toward the inner solar system one final time, capturing a mosaic of photographs that became known as the family portrait of the solar system. Earth appears in one frame as a tiny point of light, less than a single pixel in area, suspended in a scattered diffraction pattern of sunlight. Carl Sagan, who had campaigned for years to have the image taken over the objections of those who thought it would waste science time, later wrote that the image underscores the responsibility we bear for one another and the longing to continue our journey into the cosmos. After the family portrait, Voyager 1's cameras were turned off permanently, their power saved for the instruments that would matter most in the decades ahead. Both Voyager spacecraft are now beyond the heliopause, the boundary where the Sun's outflowing solar wind finally yields to the interstellar medium. The density of ionized gas around the spacecraft increased, the direction of the local magnetic field shifted to align with the interstellar magnetic field rather than the Sun's field, and the flux of low-energy solar wind particles dropped while the flux of high-energy galactic cosmic rays rose. Voyager 2 crossed the heliopause in November of 2018, and because its plasma science instruments still functioned while Voyager 1's had failed years earlier, it provided the most direct measurements ever made of the conditions at the boundary itself, On the far side of the heliopause, Voyager 1's plasma wave instrument has recorded something unexpected, a faint, steady background hum in a narrow frequency band that persists between solar events. When a solar eruption sends a pulse of energetic particles outward through the heliosphere, it creates a detectable wave in the surrounding plasma, a strong oscillation that lasts for months. But between these events, there is a quieter, continuous tone that corresponds to the thermal resonance of electrons moving through the sparse plasma of the interstellar medium, vibrating at the local plasma frequency. By measuring this frequency, researchers can calculate the local electron density, which is itself a direct measurement of how dense the interstellar medium is at Voyager's current location. The signals have been used to trace how the plasma density changes as the spacecraft moves further from the Sun. The interstellar medium is not uniform. It has structure, density variations, magnetic field gradients, and regions of turbulence. And Voyager is now mapping it from the inside, one data point at a time, as it drifts outward at roughly 17 kilometers per second. Both spacecraft carry nuclear power sources, radioisotope thermoelectric generators loaded with plutonium-238 in 1975. The generators lose power as the plutonium decays, and by the 2020s the output had declined to the point where mission controllers began shutting off instruments and heaters one by one. Attitude control, the ability to keep the spacecraft's antennas pointed at Earth, is the most critical function. A signal from Voyager 1 takes more than 22 hours to reach Earth at the speed of light, and the reply takes another 22 hours to return. Any malfunction is a 2-day conversation at minimum. Engineers estimate the spacecraft will fall silent sometime in the late 2020s, though the exact timing depends on which systems are kept active and how the hardware ages in the radiation environment of interstellar space. After the last signal, the spacecraft will continue. They will coast through the interstellar medium without power, without communication, without any further contact with the civilization that built them. In about 40,000 years, Voyager 1 will pass within 1.6 light-years of a dim red dwarf called Gliese 445 in the constellation Camelopardalis. Voyager 2 will approach Ross 248, an equally faint red dwarf, at roughly the same epoch. Neither encounter is particularly close in astronomical terms, but both represent the only confirmed future close approaches of any human-made object to another stellar system within a timescale we can meaningfully discuss. After those encounters, the trajectories carry both spacecraft on indefinitely, circling the Milky Way in the same slow galactic orbit as the Sun, moving through the galaxy for hundreds of millions, perhaps billions of years after every trace of the civilization that created them has vanished. Each spacecraft carries a golden record, a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth, along with instructions for playing it. The sounds include natural phenomena, music from dozens of human cultures, and spoken greetings in 55 languages. The images include diagrams of human DNA, mathematical relationships, and the solar system's position relative to 14 nearby pulsars, a map that any sufficiently advanced civilization should be able to decode. Whether the records will ever be found is unknowable. What they represent is knowable. The choice of a civilization at a specific moment in its development to send a message into the permanent record of the universe. The Voyagers may outlast every structure humanity has ever built, every institution, every language, every nation, every memory, and yet they carry encoded in metal evidence that something once lived here and wondered about what lay beyond. Between the rocky inner planets and the gas giants of the outer solar system lies a region of space that popular imagination often pictures as a dense, treacherous obstacle field clogged with tumbling boulders. The reality is far more spacious and far more scientifically interesting. The asteroid belt, occupying the region between Mars and Jupiter, roughly 2 to 3.5 astronomical units from the Sun, contains millions of objects ranging from microscopic grains to dwarf planets. But the total mass of all those objects combined is less than 4% of the Moon's mass. If you gathered every asteroid in the belt into a single body, it would form a world smaller than Pluto. Spacecraft have been flying through the belt since Pioneer 10 crossed it in 1972, and not one has suffered a single confirmed collision with a belt object. The belt is vast, and its contents are widely, almost invisibly scattered. The asteroids themselves are not a random collection of debris. They are sorted to some degree by composition. The inner regions of the belt contain predominantly rocky silicate asteroids, similar in composition to the terrestrial planets. The outer regions contain more carbonaceous asteroids, rich in carbon compounds and hydrated minerals, similar in composition to the most primitive meteorites found on Earth. This gradient reflects the temperature conditions that existed during the solar system's formation. The inner belt was hotter, favoring rocky materials, while the outer belt was cooler, allowing water, ice, and carbon compounds to be incorporated into growing bodies. In between, a complex dynamical history driven by Jupiter's gravitational resonances has emptied certain orbital zones, creating gaps in the asteroid distribution called Kirkwood gaps. Jupiter's gravity effectively stirs the asteroid belt continuously, preventing any further planetary growth and gradually delivering asteroid material toward the inner solar system over millions of years. The first spacecraft to orbit an asteroid was Near Showmaker, which reached the near-Earth asteroid Eros in February of 2000 and ultimately landed on it. But the most comprehensive exploration of the belt's major bodies came with the Dawn mission, a spacecraft that achieved something no probe had done before. It orbited 2 different extraterrestrial destinations in a single mission, using an ion propulsion system to make the transition possible. Dawn launched in September of 2007. Ion propulsion accelerates xenon ions to very high velocities using electromagnetic fields and ejects them as exhaust, producing a thrust so gentle it could not push a piece of paper off a table, but sustainable for months or years in the frictionless environment of space. Over time, that continuous gentle push accumulates to a total velocity change far exceeding what chemical rockets can achieve for a given propellant mass. Dawn's ion engines accumulated a total velocity change of 11 kilometers per second over the course of its mission, more than any other spacecraft in history. This made it possible to decelerate into orbit around Vesta, complete an extensive survey, then accelerate out of orbit and decelerate again into orbit around Ceres, a sequence that would have been completely impossible using conventional propulsion within any realistic mass budget. Dawn arrived at Vesta, the second most massive object in the belt, in August of 2011. Vesta is not a typical asteroid. Geologists classify it as a protoplanet, a world that began differentiating into a layered structure with an iron core, silicate mantle, and rocky crust before the formation of Jupiter disrupted its development and prevented it from accreting into a full-sized planet. A differentiation of Vesta into layers, which occurred because radioactive elements decaying in its interior generated enough heat to melt the body shortly after its formation, happened within just a few million years of the solar system's birth. This makes Vesta a record keeper of conditions in the very early solar system before planetary formation ran to completion around the inner planets. The surface of Vesta tells a history of sustained violence. The southern hemisphere is dominated by 2 enormous overlapping impact basins. The older basin, Venenia, is roughly 400 kilometers across. The younger Rio Silvia Basin, about 500 kilometers wide and 19 kilometers deep, was formed by a collision so powerful that it excavated material from the mantle beneath the crust and hurled it across the solar system. Silvia has a central peak rising 22 kilometers above its floor, making it the second tallest mountain in the solar system behind only Olympus Mons on Mars. From the center of that peak, if a visitor could somehow stand there, the distant walls of the crater would be below the horizon, too far away to see directly due to the curvature of the body. The impact that created Silvia sent shock waves through Vesta's entire structure, cracking the crust and producing a system of enormous troughs that circle the equatorial region, some hundreds of kilometers long and several kilometers deep, like the stretch marks of a catastrophic blow. The material ejected by the Silvia impact did not simply fall back to the surface. Some of it achieved escape velocity and spread throughout the inner solar system. Scientists believe that a large family of smaller asteroids known as the Vestoids, which share a similar composition and orbital characteristics with Vesta and with each other, are fragments from those ancient impacts. More compellingly, a class of meteorites called the HED meteorites for howardite ukrit diogenite are chemically distinct from other stony meteorites and have long been suspected to come from a differentiated parent body. Messenger's compositional measurements of Vesta confirmed the match. The HED meteorites are pieces of Vesta, samples of another world that fell to Earth as free gifts from the asteroid belt, waiting to be found in deserts and on ice sheets. Dawn spent 14 months at Vesta before departing. In March of 2015, after a 2.5-year transfer, the spacecraft was captured by the gravity of Ceres, the largest object in the asteroid belt and the only body in that region massive enough to be classified as a dwarf planet. Ceres is roughly 945 kilometers in diameter, accounting for about a third of the asteroid belt's total mass. It is massive enough that its own gravity has pulled it into a nearly spherical shape, distinguishing it from the irregular lumps of most asteroids. Where Vesta is dry and geologically ancient, Ceres is wet and arguably still active. Dawn's instruments detected water ice near the surface in permanently shadowed polar craters, hydrated minerals throughout the regolith, indicating that liquid water was once abundant in the interior, and ammoniated compounds that present a compositional puzzle. Ammonia requires the cold of the outer solar system to be incorporated into solid material during planet formation. Its presence on Ceres suggests either that the dwarf planet formed much farther from the Sun in the cold outer solar system and migrated inward to its current orbit through gravitational interactions during the solar system's early reshuffling, or that material from the outer solar system was delivered to Ceres by cometary impacts over billions of years. Either possibility has significant implications for models of how the solar system's architecture evolved. The most visually dramatic discovery at Ceres was a set of exceptionally bright spots concentrated in the floor of a crater called Occator, about 92 kilometers across. From Earth, Hubble Space Telescope images had shown Ceres as a slightly oblong fuzzy blob with some brighter patches, tantalizing but unresolvable. From orbit, dawn revealed more than 300 bright spots scattered across the surface. Spectral analysis confirmed they are deposits of sodium carbonate and other evaporite salts, left behind when salty water welled up from a subsurface reservoir and sublimated into space in the near vacuum at the surface. The brightest deposits in Occator crater, named Cerealia facula at the center and Vinalia faculae elsewhere on the crater floor, are geologically fresh, perhaps only a few million years old. Their freshness implies that the process that created them is ongoing or very recently active, driven by heat from the impact that formed Occator itself, or by residual internal heat from radioactive decay, or both. Ahuna Mons, a dome-shaped mountain rising about 4 kilometers above the surrounding plain, is the most visually striking evidence for active internal processes on Ceres. Its deep flanks are surprisingly smooth and bright compared to the heavily cratered terrain around it, suggesting that it is geologically young. A structure made of ice and salt would gradually slump and flatten under its own weight at Ceres' surface temperature over hundreds of millions of years, erasing the steep slopes. Ahuna Mons still stands crisp and steep, which constrains its age to at most a few 100 million years. It is most likely a cryovolcanic dome built up by the extrusion of material from a subsurface brine pocket, analogous to the way silic lava domes form on Earth when viscous magma pushes up through a vent without erupting explosively. If this interpretation is correct, Ahuna Mons would be the best confirmed example of cryovolcanism in the inner solar system. Dawn also confirmed the presence of organic molecules on Ceres' surface, concentrated in a region near a fresh impact crater. The source of these molecules is unclear. They might have been delivered by the impactor, synthesized by chemistry in the subsurface, or concentrated by some process that accumulated organics from the surface over time. Whatever their origin, they add to the picture of Ceres as a body that has been chemically active throughout its history, harboring the ingredients that astrobiologists consider relevant to the question of life's origin and distribution. On October 31st, 2018, Dawn exhausted its hydrazine propellant and lost the ability to point its antenna toward Earth. Communication ceased, and the mission was formally ended. Over the course of its 11-year operational life, Dawn had traveled more than 6.5 billion kilometers, entered and departed orbit twice, captured 69,000 images, and transmitted 132 gigabytes of scientific data. It now orbits Ceres indefinitely on its final trajectory, expected to remain in orbit for at least another 20 years before any risk of impacting the surface. These worlds, Mercury and Venus, Saturn and its rings, the Voyagers crossing into interstellar space, Vesta and Ceres in the asteroid belt, share one quality above all others. They are not what anyone expected. Every mission that has visited them has returned surprises that the best models of the day failed to predict. Mercury has a magnetic field and ice at its poles. Venus had an ocean once, maybe. Saturn's rings are younger than dinosaurs. Io has active volcanoes. Ceres has briny water welling up from inside. The solar system has been studied continuously with spacecraft for over 60 years, and it continues to generate discoveries that reshape the questions we thought we already knew how to ask. This is the nature of exploration and of science more broadly. The closer you look, the more you find, and the more you find, the more clearly you see the edges of what you do not yet understand. The solar system is not a known place. It is a place we are still learning to see, and every spacecraft we send out extends the range of human perception a little further into the dark. The asteroid belt is not merely a collection of leftover rubble. It is an archive. The bodies in the belt formed in the same region of the solar nebula that produced the terrestrial planets from the same reservoir of material at roughly the same time. But while the inner planets underwent dramatic geological processing over billions of years, melting and remelting their interiors, erupting volcanic material, cycling rock through tectonic processes, and in Earth's case developing a biosphere that chemically altered the crust, ocean and atmosphere, many asteroids have remained essentially unchanged since the solar system's first 10 million years. They are time capsules preserving original mineral assemblages, isotopic ratios, and organic compounds that have long since been erased from planetary surfaces by subsequent geological activity. Meteorites that fall to Earth from the asteroid belt give us physical samples of this ancient material to study directly in laboratories. Carbonaceous chondrites, the most primitive class of stony meteorite, contain amino acids, the molecular building blocks of proteins, as well as nucleobases that form the structural backbone of DNA and RNA. These molecules did not form in the meteorites themselves. They were present in the original solar nebula, synthesized by photochemical reactions in the cold outer disk, and incorporated into the first solid bodies as they accreted. Their survival inside meteorites for 4.5 billion years demonstrates that the chemistry of life is not uniquely terrestrial. The ingredients are distributed throughout the galaxy, produced by processes that require no life at all. What remains to be understood is what specific conditions are needed to organize those ingredients into something that can replicate and evolve, and whether those conditions are common or rare. The asteroid belt also contains clues to one of the most consequential and poorly understood episodes in Earth's history. Geologists call it the Late Heavy Bombardment, a period roughly 4 billion years ago during which the inner solar system appears to have experienced a dramatic increase in large impacts. The lunar highlands are saturated with impact craters from this period. The oldest rocks preserved on Earth, which are very few, also bear the chemical signatures of large impactor strikes. The cause of the bombardment is debated. One influential model, developed by a group of researchers working at the Côte d'Azur Observatory in Nice, and now called the Nice model, proposes that the giant planets underwent a period of orbital migration after the solar system formed, with Jupiter and Saturn shifting inward and then outward again in a gravitational dance that scattered material from the outer asteroid belt and the outer solar system inward toward the terrestrial planets. If the NICE model is correct, then the asteroid belt as we see it today is significantly depleted relative to its original population. And the large impacts that scarred the Moon and sterilized whatever early life might have been present on Earth were caused by material disturbed from the outer solar system by giant planet migration. The distribution of asteroid spectral types in the present-day belt can be compared against predictions from different migration models, and Dawn's compositional data from Vesta and Ceres contributed specific data points to this ongoing investigation. Ceres' story in particular may be a chapter in the larger history of what planetary scientists call the ocean worlds of the solar system. In the outer solar system, the moons of Jupiter and Saturn have revealed that liquid water is not confined to Earth's surface. Europa almost certainly harbors a global subsurface ocean beneath its icy shell, kept liquid by tidal heating from Jupiter. Enceladus, one of Saturn's smaller moons, was found by Cassini to be actively erupting a plume of water vapor and ice from its south polar region, fed by a subsurface ocean of liquid water that contains sodium, silica, nanoparticles, molecular hydrogen, and organic compounds. The molecular hydrogen in particular is significant because it indicates ongoing hydrothermal reactions between water and rock at the seafloor, a process that on Earth supports entire ecosystems of microbial life that never see sunlight. Titan has surface lakes of liquid methane, but also, according to some models, a subsurface ocean of liquid water deep beneath the ice. Ganymede and Callisto may have interior oceans as well. The solar system, it turns out, contains far more liquid water than its surface appearances suggest, almost all of it hidden beneath ice shells on bodies, once dismissed as frozen and lifeless. Ceres fits into this picture as a transitional case. It is too small and too warm, at its distance from the sun, to maintain a fully global ocean today. But the chemical evidence preserved in its surface, the carbonates, the ammoniated compounds, the bright salt deposits, and the hydrated minerals, reads like a geological memoir of a time when liquid water was abundant inside the body. Ceres may be a desiccated ocean world, a body that once had what Europa or Enceladus have today, but has since lost most of its internal heat and allowed its interior to freeze. The liquid water that remains, if any persists, is likely concentrated in pockets or pores in the deep interior, rather than a global ocean. Understanding Ceres's current state and past history helps scientists build models of how ocean worlds evolve over time, which in turn informs estimates of how long the potentially habitable conditions inside icy worlds like Europa or Enceladus might persist. The missions described here across Mercury, Venus, Saturn, the interstellar boundary, and the asteroid belt were not planned as a coordinated program. They were individual projects conceived in different decades by different teams in different countries, funded by different agencies through different political pressures, built with the technology available at the time of their development. Yet taken together, they form something like a portrait of the solar system as it actually is, which turns out to be vastly more complex, more violent, more chemically rich, and in some respects more potentially hospitable to life than any model available before the space age would have suggested. Understanding planetary history matters beyond pure scientific curiosity. Earth is not an isolated world developing in a vacuum. It has been shaped by its membership in this solar system by the delivery of water and organic material from the asteroid belt, and outer solar system by the gravitational influence of Jupiter, which shields the inner planets from some fraction of the cometary bombardment that would otherwise reach us by the Moon, whose formation in a giant impact early in Earth's history set the conditions for the stable axial tilt that may have contributed to long-term climate stability, and by the Sun itself, whose gradual brightening over 4 billion years has required the carbon cycle and the biosphere to continuously adjust to maintain habitable temperatures. Each of the worlds we have visited with spacecraft is a variable in this larger equation. Venus shows what Earth might look like if the carbon cycle had failed. Mars shows what might happen when a planet is too small to sustain a global magnetic field and loses its atmosphere to solar wind erosion. Mercury shows what is preserved when a world loses most of its outer layers and shrinks to a dense metallic remnant. There is something important in the fact that every mission discussed here eventually ran out of power or propellant and fell silent, but not before doing something that will outlast its operational lifetime by centuries. Mariner 10's measurements of Mercury's magnetic field launched decades of theoretical work on planetary dynamos that continues today. The Venera lander's photographs of Venus, a few dozen images taken over a few dozen hours total, remain the only ground truth we have for models of Venusian geology, and remain the most important data from the surface of any planet other than Earth or Mars. Cassini's measurements of Saturn's ring mass, taken in the final months of its life, settled a question about the age of the rings that had been debated for over a century. Voyager's detection of the interstellar plasma hum is actively informing the design of future interstellar probe concepts. Dawn's mapping of Vesta and Ceres created the first detailed geological understanding of the two largest asteroid belt objects in history. Science does not advance by accumulation of facts alone, it advances by the formation of better questions. The more precisely we measure Mercury's magnetic field, the more sharply we can phrase the question of why it exists. The more detail we have about Venus's surface chemistry, the more specifically we can ask whether Venus was ever habitable. The more accurately we know Saturn's ring age, the more precisely we can constrain models of moon formation and destruction. Every measurement that narrows an uncertainty also reveals the shape of what we still do not know, and that shape is what guides the next mission. The solar system is, on cosmic scales, an unremarkable planetary system. It orbits an unremarkable star in an unremarkable region of a galaxy containing several 100 billion stars, which is one of perhaps 2 trillion galaxies in the observable universe. The processes that form the Sun and its planets are not unique. They occur continuously throughout the galaxy, producing planetary systems of enormous variety. Astronomers have now confirmed the existence of more than 5,500 planets orbiting other stars. and the statistical extrapolations from those detections imply that there are more planets than stars in the Milky Way. Rocky planets in the habitable zones of their stars, where liquid water can exist on the surface under the right conditions, appear to be common. But common does not mean understood. We cannot yet measure the atmospheric composition, geological activity, magnetic environment, or interior structure of any exoplanet with the precision that decades of solar system exploration have given us for our own 8 planets and their moons. The solar system is the laboratory where the tools and concepts are developed that will eventually be applied to other planetary systems. Every mission that maps a crater on Vesta or measures a salt deposit on Ceres or listens to the hum of interstellar plasma is contributing indirectly but genuinely to our eventual capacity to understand the broader universe we inhabit. The next generation of missions is already being planned and built. Baby Colombo will spend years at Mercury filling in the gaps left by Mariner 10 and Messenger. The Da Vinci probe will descend through Venus's atmosphere, measuring its chemistry in unprecedented detail. The Europa Clipper spacecraft, launched in October of 2024, is en route to Jupiter and will conduct dozens of close flybys of Europa, measuring the depth and salinity of its subsurface ocean, mapping the thickness of its ice shell, and searching for the kinds of chemistry that might indicate biological activity. The Dragonfly rotorcraft mission to Titan, currently in development, will fly across Titan's surface, visiting multiple sites and studying the prebiotic chemistry in Titan's sands and dune fields, searching for signs of whether the chemistry of life is underway there. The New Horizons spacecraft, having completed the first detailed exploration of Pluto in 2015 and the Kuiper Belt object Arrokoth in 2019, continues outward through the Kuiper Belt, transmitting data. Mars has been explored by rovers, orbiters, and landers for over 5 decades and continues to yield discoveries about its ancient water-rich past and its current habitability potential. The trajectory from the first tentative Mariner 10 flyby of Mercury in 1974 to the current fleet of active solar system missions spans exactly 50 years. In that time, humanity has placed instruments on the surfaces of Venus, Mars, and Titan. We have orbited Mercury, Venus, Mars, Jupiter, Saturn, Vesta, Ceres, and multiple asteroids and comets. We have sent probes through the atmospheres of Jupiter and Saturn and into the tail of a comet. We have landed rovers that have driven tens of kilometers across Martian terrain, drilling into rocks, analyzing chemistry, and taking photographs of sunsets on another world. We have reached the interstellar medium, and we are still just beginning. Every answered question opens a corridor to the next one. And the corridors do not narrow, they expand. The universe is not a puzzle that will eventually be solved. It is an inquiry that, as best we can tell, has no final answer. Only deeper and deeper engagement with a reality that exceeds whatever framework we bring to it. That is not a limitation. It is an invitation